and start from the current slide. And we were going to start on example 2, but before we get started, any questions from anything we've done so far? I think what I'll do is go back one slide, okay, and turn on the projector even maybe. That might be a clever idea. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 4, 7, 8, 9. Yeah. I haven't quite broken double digits yet, but hopefully we'll get here. And one of these days is for. Ah, there we go. Okay, 3's here, right? And hey, all right, good deal. Anyone else slip in what I wasn't looking? Okay. All right. Just a little bit of review. Definition of periodic functions: anytime a function evaluated at some value plus a constant is always equal to the same, has the same value as the function at the value before you added the constant. For no matter what, for all the t's in the domain, that means this function is going to repeat itself and repeat itself and repeat itself. That means it's a periodic function. The smallest of those c's for which that's true is called the period of that function. And then they snuck this one in on the bottom. We know that a function is even when f of t of negative t is the same as f of t. That means whatever you do on this side, same thing on this side, so it's the same on both sides. Even function. Odd if it's exactly the opposite on both sides. Now, in most functions, back in pre-calculus algebra, most functions were actually a neither one of those. In trig, unless you have what they call a horizontal shift, which we'll be calling a phase shift, then all the trig functions are even, or odd, either even or odd. With cosine and secant, the reciprocal functions there being even and the other four being odd. Because they're periodic functions, they do the same thing over and over, and if they do the same thing on either side of the y-axis, they're even. If they do the opposite things, like sine and tangent, they're reciprocals. They're odd functions. So, hate it when they work the problems for you. The question is, I can't think of a way to cover that and get it all done. Because 13 pi 6, okay, 13 6 pi, however you want to say it. You can divide 6 into 13 and you get 2 with 1 left over, right? So that would be 2 pi plus 1 pi left over. Well, because that's true, the sine of 13 6 pi is going to be exactly the same as, of course, 13 6 is that. So therefore, what can you tell me? That will also be the same as sine of what? Is it patience? No. It's Jemiah? Okay, Jemiah. And Demetrius here. All right, anyone else come in since I called roll? Okay. All right. Anyone come up with anything? That would be the same as sine of what? Any guesses? Second?
Which one are you talking about, the second one?
What is, okay, this is equal to that because those two are equal, right? What is this also equal to? You could put one more equal sign out there.
Would it be 3 pi over 6?
Sine of pi over 6, exactly. Whoa, let me get my color back. Okay, And why is that? The reason for that, anyone know what that reason is? Sort of a two-part reason. Okay, yeah, that's how we got from here to there, yeah, from up there. Why is this true, though? Why is this, which of course is the same as this, equal to that? Because sine is what kind of a function? Periodic function with a period of 2 pi. All right. 30, 23. Is it Devin? Devin? Yeah. Okay. Anyone else come in since the call? Okay. Those are the reasons. Sine is a periodic function, and its period is 2 pi. So therefore, every time you add 2 pi to a value, you're going to wind up with the same thing. Well, 2 pi is one time around the circle. One time around the circle, okay? Every time you add 2 pi to it, you wind up right where you are with the same x and y values on that unit circle. So it's got to be the same. Make sense? All right. Which is sine of pi 6, okay? And I forgot to ask that part. What is the sine of pi 6? Oh, yeah, so y'all read well. Okay, good. Okay. Sine of pi 6 is the y value, which is 1/2. Okay, very good. All right, forgot we knew that. All right, how about this one? Negative 7/2 pi. You can divide 2 into 7, you get 3.5. But that would be a minus 3 pi minus 1/2 pi. We don't want 3 pi because sine is not periodic with a period of 3 pi or pi. Its period is 2 pi. So we need to have some multiple of 2 pi here. So let's make it minus 4 pi. Minus 4 pi is minus 8/2 pi. So minus 8/2 pi plus 1/2 pi will give you minus 7/2 pi. This is a little weirder way to do it, but it is correct. This is exactly 2 periods in the opposite direction, okay? So therefore, cosine of minus 7/2 pi is the same as cosine of minus 4 pi plus pi halves. And because the period is 2 pi, you can wipe this out. That's the same as cosine of what? Cosine of what? Pi over 2. And what is the cosine of pi over 2?
1.
Okay, sine of pi over 2 is 1. Cosine of pi over 2 is 0, the x value. Pi halves is straight up, the x is 0 there. All right. And here we have second patient. Yeah. Got it.
Are you always going to use like full pies, like 2 pi, 4 pi?
Any multiple of 2 pi.
Yeah.
Okay.
Like it's
2 in pi. Yeah, it has to be a multiple of 2 pi. That's why minus 3 pi wouldn't have worked for you here. Because you have to have a multiple of the period. Now, sines and cosines, the period is 2 pi. We haven't gotten there yet, but tangent and cotangent, the period is pi. So minus 3 pi would have worked if this was a tangent function. But for a sine or cosine, you need an even pi. Yeah. Okay? Which made this sort of artificial. I mean, that's really stretching it. Okay? I think what I would have done instead, without doing that first part, if they said, what is the cosine of negative 7/2 pi? Well, I would start here and go, negative 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi, 5/2 pi, 6/2 pi, 7/2 pi, there you are at pi halves. Okay? They wanted to do it this way. Which, to me, is a little convoluted. Basically, you know what your answer is and you do this again.
Yeah.
And that's not very fair. Or actually, I think the better way, another way to do it is subtract 2 pi from this. This is 3.5 pi, negative 3.5 pi. Well, add 2 pi to it. Now you get negative 1.5 pi. Okay? Negative 1.5 pi is positive 1.5 pi. Yeah. You're up there at the same place. That's how I think I would have done it, rather than off the bat saying, oh, that's negative 4 pi plus 1.5 pi. That's true. It absolutely is true, but I'm not sure I would have thought of doing it that way or even considered doing it that way. So let's see what they got. That's the same as cosine of pi halves, which is 0. Okay. The third one, the C one here. Now this time they're going sort of the other way. Well, this is asking about something different. Sorry about this. For sine of t equal to 4/5, what is sine of negative t? Why? Oh, sine is an odd function. Okay. So if sine of t is 4/5, sine of negative t. Remember how sine looks? Whatever it's doing on this side, it does the opposite on this side. So therefore, a negative t will be exactly the opposite of this. So it will be negative 4/5. I hate it when they give you the problem and say, okay, this is your example. Well, you did all the work for us. You didn't have us do any. That's not very fair, is it? Okay. So there was example 2. After every example, you'll find a checkpoint, and please do the checkpoint soon after class as you can. Make sure you refresh in your mind what's going on, because right now I'm doing all the performing. You're hopefully thinking it through, but do it on your own. Now, when evaluating a trig function with a calculator, you have to be careful and realize a couple of things. Number one, calculators will calculate trig functions, but you have to tell it what you're measuring. Are you measuring in degrees? Or are you measuring in radians? Most of this course we'll be doing in radians. You have to tell your calculator that. Now, some of the scientific calculators used to always put up DEG or RAD. You'd see that on the screen and you know what mode they were in. Most of the graphic calculators, however, don't do that. You have to go to the mode key and then find degree or radian and figure out which one you're in, or put it in one you need. Telephones, on the other hand, they have their own syntax. You have to know how to operate your own phone. So if you're using your phone, you have to know how to get back and forth and make sure you're in the right thing. So that's the first thing you do when you're evaluating a trig function with a calculator or a phone. Better be in the right mode or you're going to get some very, very wrong answers. Okay? Most calculators do not have keys for cosecant, secant, and cotangent functions. Therefore, we can't do them, right? Wrong. Because what are the cosecant function, the secant function, and the cotangent function? They're reciprocals of, what's that reciprocal of? Second? Sine, that's reciprocal of cosine, this is reciprocal of tangent. So therefore, if you're trying to find that, then do it for the reciprocal function, then use the 1 over key. Okay? X to the minus 1 key is one way to express. Some of the older calculators have 1 over x key. Okay? Now, if you don't have either one of those, just divide by it. Okay? That is taking a reciprocal. Okay? And you can go from there. So let's do a few. And here again, they do it. Well, no, here's an example. The cosecant of pi eighths. How would you do that? Go to cosecant on your calculator. Okay, do that. See what you get. No, okay.
Well, I guess you put the parentheses first, and then you put cosecant.
Find that on your
No
calculator.
cosecant. Okay, yeah, I see what you're saying.
Yeah, it's not there. So how do you do it?
I just start with sine.
Yes, it's 1 over sine of pi 8. Cosecant is a reciprocal of sine. So you can find sine of pi 8. Well, now maybe you were telling me this. First, do the pi 8s. Okay, depending on what type of calculator you have. If you have an old scientific calculator, you have to enter the argument first and then do the trig function. Most of the graphic calculators, and I think your phones, all do, you do sine first, then do it. That will open a parentheses for you most of the time. And then you do pi key. You all have pi keys on your calculators now. Divided by 8, close that parentheses. And that will give you the sine of that, and then reciprocate that, 1 over that. Okay? And that will give you the cosecant. Now, remind me, what value should you expect to find the cosecant of pi 8 to be? Just a general rule. Second? Okay. Opposite of what? Usually opposite means negation. That's not what I'm talking about here. Cosecants are always going to have a value of 1 or greater, and since this is in the first quadrant, it will be 1 or greater, or -1 or less. They will never be between -1 and 1. Secant and cosecant, never between -1 and 1. They could be -1, they could be 1, but then they all go in the opposite direction. Sines and cosines, on the other hand, are always going to be between -1 and 1. They can be -1 and +1, but they'll never be outside of it. So you expect an answer here, because this is the first quadrant, to be positive, and this will be a number greater than 1. Greater than 1. Now, I can't tell you what it will be, but it'll be a number greater than 1. Okay. So here's how they suggest you do it. Now, if your phone has a different syntax, do it. Now, they start with a parenthesis. I think that is unnecessary. But the way they're doing it, it would be necessary. Then you do sine. That automatically, most of the time, will open the second parenthesis for you. Then you do pi divided by 8, and you have a pi key, division by 8. Close this parenthesis out. Then close that one out. That actually calculates it for you. Then press the reciprocal key, or the 1 over x key, or the x to the -1 key. And that, then I don't even think you need to press enter. I think when you press that key, it gives you the answer. Okay? Is that what you get? Okay, good deal. Notice that's greater than 1. Never get an answer 0.161. Not for a cosecant. Ever. 1 maybe, but always going to be greater than 1 in the first quadrant, and it could be less than -1 in some of the other ones. Okay, does that make sense? All right, now they give us something to do, and they show you how to do it. Okay, now, sine of 2/3 pi. What's the first thing you check? Yes, in what mode? Radian mode, okay, because why do you know that's in radian mode? Why do you know it's in radian mode?
So it's 2 pi.
Okay. Okay, now, that's exactly what I think most of the time. It has a pi in it. And you're absolutely right. Most of the time if it has a pi in it, you're going to be in radians. It's not necessary, though. The thing that tells you this is in radian mode is there's no degree symbol. To be in degree mode, you have to have a degree symbol. If there's no degree symbol, you got to be in radian mode, whether there's a pi in there or not. Okay? So first you're in radian mode. Good deal. All right, what do you enter? What do you enter?
We do they're doing the open parentheses first.
Okay, in this one you don't have to, but you could if you wanted to. Just press the sine key. Okay? And then it usually opens the parentheses for you, but some of your phones it may not. If it doesn't, you have to open that. And then you put 2 pi divided by 3. You have to, well, it's a good idea to close that one. And I believe you do have to press enter for that. Is that a reasonable looking number? Why?
It's not greater or less.
It's what?
It's in between.
It's in between -1 and 1, and because this is in which quadrant? 2/3 pi. Not first.
Second quadrant.
Second quadrant, what is sign? The SIGN of the SIN in the second quadrant. The sign of the sign. All students take calculus. Sign is positive in the second quadrant. So yes, you expect that to be positive. Remember that little acronym? Oh, you don't remember that. Your 4 quadrants. All your trig functions are positive in this one. All students sign is positive here, and its reciprocal, which is the reciprocal sign, cosecant, take, tangent, and its reciprocal, cotangent, calculus or chemistry or whatever. What is that? Those are the 3 big functions. Cosine, and its reciprocal is secant. Okay. So those, yeah. I also have heard it said all state technical college. There's all sorts of things you can use for that, but that reminds you what the signs are in the various quadrants. Okay? Now, how about this one? Cotangent of 1.5. What mode are you in? Don't read my hand. Radian mode, okay? You read my hand, didn't you? I could tell, okay. Why? There's no pi in it,
There's no degree.
but there's no degree sign. It must be radian, okay? What would you enter?
Parentheses.
Okay, you do have to have a parentheses here, do it the way they do anyway.
Tangent.
Then you do the tangent,
And then
1.5. Oh, it usually opens that parentheses, 1.5, but you have to close it and then do what?
Another equivalent.
Yeah,
And then the reciprocal.
and then do the reciprocal. Okay. I don't think you need an enter on that one, but maybe your calculator does. Here's how I do it because I don't usually lead off. I would just do the tangent key, opens this one, 1.5, close that one, and then I press enter then. It gives you a number, and then I hit the reciprocal. And it gives you the answer. I'm lazy. That's one fewer keystroke than the other way. So I'm really lazy. Okay. Now, what do you expect for cotangents? What do you expect your values to be? It can be anything from negative infinity to positive infinity. No way to tell. Except, where are you, Waldo? That one's sort of tough. Okay? What is your vertical line? What is that angle?
9 degrees.
Okay, but we're in,
Radian.
okay, in radians, what are you? Pi halves. And what is pi? Don't know that one. 3.1416 approximately. Okay? So half of that is 1.57. So you're still in the first quadrant there. So therefore your first quadrant is expected to be positive, sure enough it is. And because you're barely in the first quadrant, now we haven't talked about the graph of the cotangent yet, but you'll see it's very close to 0 there. So that is close to 0. If that was a tangent, if that was a tangent, you're going to have a huge number there because, because you're close to pi halves. Pi halves is that vertical asymptote, remember? So you're going way high. Someone do tangent of 1.5 radians. You'll see it's a huge number. Someone do it real quickly. Tangent of 1.5. Well over 10, right? 14, okay. Pretty good number. Okay. I think that's all. Yes. Okay. There is a checkpoint. Please do the checkpoints as soon as you can after class. Make sure you got it in your brain what these are. And let's do vocabulary. Top of page 275. Each real number t corresponds to a point xy on the blank blank. What's the title of this section? Unit circle. There we have it. Okay. Number 2. A function f is blank when there exists a positive real number c such that f of t plus c is equal to f of t for all t's in the domain of f. What do we call that function f? F of t plus c is always equal to f.
Periodic.
A periodic function, exactly. Is periodic. Number 3, the smallest number c for which a function is periodic, there's our answer for before, is the blank of f. Leave off the IC. Period, the period of c, everybody? Okay? A function f is blank when f of minus 1 is equal minus t is equal to minus f of t. What is that? It's what? I can't hear. If f of minus t is minus f of t, that's odd. You're going in the opposite direction. And it's blank when f of minus t is the same as f of t. Even. Got it. Homework exercises here. Do either 5 or 7. They're both at calcchat.com. Do either 9 or 11. They're both at calcchat.com. Do any of the odds 13 to 21. They're all at calcchat.com. Then do any of the odds 23 to 29. They're all at calcchat.com. 23's at calcview. Do any of the odds 31 to 35. They're all at calcchat. 31's at calcview. Do any of the odds 37 to 41. They're all at calcchat. 37's at calcview. And using a calculator, do any of the odds 43 through 47. They're all at calcchat. 49's at calcchat. I would do that one. And then there's an exploration here, true or false, 51 and or 53. They should be at calcchat. And there's a conjecture that you can do if you'd like. I don't know if it's at calcchat. It ought to be, but it may not be. 55. There's an error analysis at 57. Now that, what they've got there is wrong. You tell why it is. I don't like that too much, but I think there is some benefit in doing that. That's 57. And then using technology, if you want to try to do that, you can, 59. You can think about doing 61 if you'd like. All those odds should be at calcchat, but I can't guarantee that think about it. Some of those others are. So check them out and see. Any questions? 4.2. Okay. Let's move to 4.3. Well, one of these days it will. We'll get there. All right. It is really slow. There we go. All right, we're still in Chapter 4, Trigonometry, the measurement of triangles. And this time we're actually going to do triangles, okay? Last term, we were doing circles, not triangles. We'll do right triangle trigonometry, okay? Here is the big difference. When we're on the unit circle, we're staying, our points that we're dealing with were always how far from the origin? 1 unit from the origin. Now we're going to do right triangles. These could be huge right triangles or tiny right triangles. They could have hypotenuses that would be huge or tiny. Or they could be 1. But the odds are they won't be always 1. That's the difference. Okay? And this is where, back when I first was learning trig, we always started with right triangles, and then we did unit circle just to fill in. And I really liked it better that way because this gave you all the possibilities and then said, but for unit circles, notice here, the hypotenuse is always 1. And that made everything make sense. Now I've seen students before say sine is y. Not in right triangle trig. That's only when you're on the unit circle. Okay, we'll get to that later. Our objectives here are to evaluate trigonometric functions of acute angles. What are acute angles?
Under 90 degrees.
Yes, between 0 and 90 degrees. And we use a calculator to evaluate trigonometric functions, which we've already done. We'll use the fundamental trigonometric identities, which are the same as they were for unit circle. The identities are identical, okay? And we'll use trigonometric functions to model and solve some real-life problems. Good, okay? So let's go back over the 6 trigonometric functions, but this time we're going to do it relative to right triangles, not unit circles, okay? So let's first introduce a right triangle. Hi, right triangle, here you go. This section introduces the trigonometric functions from a right triangle perspective. Consider this right triangle with one acute angle, okay? We're going to call that theta. And as shown here, relative to that angle theta, you have 3 sides of the triangle, right? Now, so right triangle, so one of these angles is a right angle, okay? Now tell me, is that going to be the smallest, the largest, or the middle angle of that triangle in size? That right angle.
Should be the larger.
Why?
It's a right triangle, so it's gonna have 2 acute angles.
Okay. Let's just say any old triangle. What's the sum of the 3 angles? 180. Now, if one of those is 90, that means the other 2 have to add to be 90, so neither one of them can be greater than 90, right? So, this, if that's acute, that one's got to be acute if that's right, right? Got to be. Okay. So, you're absolutely right. This is the largest angle. What does that tell you about the sides? The side opposite the largest angle is going to be the, and it is the hypotenuse if that's a right angle, but for any triangle, the side opposite the largest angle is always the longest side. The side opposite the smallest angle is always going to be the shortest side. And the side opposite the middle angle is just right. No, it's going to be the middle one. Okay? Always. Small angles, short sides. Big angles, long sides. Okay? Middle angle is going to be the middle side. Okay? So, on a right triangle, that long side is called the hypotenuse. Okay? Opposite the right angle. Okay? Now, since we chose one of these acute angles to be theta, then there's always going to be a side opposite that. That's not going to be the hypotenuse, because the hypotenuse is opposite the right angle, right? So this is going to be one of the shorter sides opposite that angle. Well, if that side is opposite the angle, this one's adjacent to the angle, right? Because it touches the angle. It's opposite the angle. And that's the hypotenuse. Okay? So we're going to call them by those names. Opposite side, adjacent side, and hypotenuse, relative to whichever angle we happen to choose. We don't choose this one. That's the right angle. That's always the hypotenuse. Choose one of the acute angles. Both of them got to be acute. Choose either one of them, then one. The side opposite is its opposite side, and the side adjacent to it is its adjacent side. If we had chosen this angle, then this would be the adjacent side. That would be the opposite side. Okay? That's always the hypotenuse. Okay. Now, you got what we call it. Now, using the lengths of those 3 sides, you can form these 6 ratios, same as we did before, sine, cosine, tangent, cotangent, secant, cosecant, to identify these 6 trig functions. The difference here is we're not on the unit circle, so the hypotenuse is not always 1. We never said that before. I think I said it, but that was the key. Now we're going to use the 3 sides. Okay? You need that a little longer? Sorry. I thought we were going to do something down here. while y'all are writing, I'll go and do it. The sign, let me get my pen color back, okay? The sign is always the opposite side over the hypotenuse. The cosine is always the adjacent side over the hypotenuse. Now this is of the angle theta, whatever theta you're choosing. The tangent is always, anyone know? Opposite over adjacent. And then cotangent, guess what that is? The reciprocal of what? The tangent. So this is going to be adjacent over opposite. That's not a zero, that's a O. Okay, you can't divide by zero. Okay. The secant is what? The reciprocal of what? Cosine. So this will be hypotenuse over adjacent. And the cosecant is the reciprocal of the sine, which is going to be hypotenuse over opposite. Okay? Now, remember what I said about secants and cosecants? They're always greater than 1 or less than -1. Why is that? Well, the hypotenuse, by the way, is always positive. By definition, the hypotenuse is always positive. Your other sides can be positive or negative. We're not there yet, but we will be. But this is always positive. So the hypotenuse is always longer than the opposite side. It's always longer than the adjacent side for a right triangle, right? Gotta be. It's the longest side. So therefore, this is going to be a number greater than 1. That's going to be a number greater than 1. Absolute value greater than 1. These are always going to be less than 1. Less than 1. These you can't tell. Okay? So there's no telling on the tangent, cotangent, they could be anything. All right. Now you want my first time I taught, I think it was the first time I taught this course, a trig course, went back over at Western State Technical College. I was up here in this room, and a gal who sat right back there, behind, right next to Bree over there. Okay, when we did this, sine, cosine, and tangent. This is how I remember them. I remember them as sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's just how I learned them. That's how I remember. I didn't need it. But I had a roommate in college. He was an undergrad when I was in grad school. And he found this helpful. And I've seen it in other places too. To me, I had to know what I was saying. He did this. Sa, ka, toa. Only he wrote it all together. And frankly, when I say sa, ka, I can't tell which is the O and which is the A. So I have to know which is adjacent, which is hypotenuse. So that was no help to me. But this is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. He found the toa makes sense. The sa, ka, I have to say, wait, is that an A or an O? Yeah, sine is opposite over the hypotenuse. I know that. Okay. Yes.
I learned that, but also I pronounce sa as so.
Oh, okay.
Yeah,
So katoa.
So katoa.
So katoa. Okay. So that helps it some.
Some old hippie caught another hippie tripping on acid.
Okay, say that one more time.
Is some old hippie caught another hippie tripping on acid.
Okay, he's from the 60s. You can tell. No, okay. That is a good one. I think now that you say that, I have heard that one before, but I had forgotten it. But this gal that was back there sitting next to Bree, but she's not there anymore, she said, some old hag caught another hag taking oats away. I went, okay. I mean, I can remember that. And maybe some old hippie caught another hippie tripping on acid. That's it, okay. If you can remember that, that's fine. But the one or two terms later, then another student, I don't remember where she said some old hen caught another hen taking oats away. I like hens better than hags, so I went with that one. So that's my favorite. There's lots of ways you can remember that. So katoa, some old hippie, or some old hag, or some old hen, but that's easy to remember those. and then just remember the others are reciprocals. Okay? There's no mnemonic device for that. Okay, have I killed enough time to go to the other slide? Okay. All right. In the following definitions, it's important to see that if you're in the first quadrant, which, guess what? If you got a right triangle, you're in the first quadrant. Theta has to be an acute angle. Theta lies in the first quadrant. And for such angles, the value of each trigonometric function is positive because the opposite side is positive, the adjacent side, whichever those are, and the hypotenuse is always positive. Okay? So here are the definitions, and these are the ones I always use, even on the unit circle. On the unit circle, the hypotenuse is 1, 1, 1, 1. That's just always 1. Okay? But any other time, it's this. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then, like we just talked about, this is reciprocal of that. So cotangent is adjacent over opposite, secant is reciprocal of cosine, which is hypotenuse over adjacent, and cosecant is reciprocal of sine, hypotenuse over opposite. So, when you don't have the unit circle, be sure you put 1, don't put 1s here, put hypotenuse. Before we just said this is the y value. We said that's the x value. That's because the hypotenuse was always 1. The radius was always 1. Okay? Not true anymore. And we said this was 1 over y and this was 1 over x. Don't use that anymore. Use this. Okay. Make sense? OPP. I just do H, O, and A. They do OPP, ABJ, and HAYP. Much easier to just do the first letters. All right. Get that. This will do you. This will take care of you. Big time. All right. So here's example 1. Use a triangle in this figure to find the values of the 6 trigonometric functions of theta. Okay? Here's your theta. So you tell me, what are the 6 trig functions? Sine, cosecant, you must read the book, cosine, secant, tangent, and cotangent. All right, what is sine? So, some old hippie. Okay, opposite over hypotenuse. What's your opposite in that triangle? Here's your theta, right there. Opposite would be 4. What's the hypotenuse? We don't have it. Oh, we can't do this, can we? Or can we? Say again? Of course we can. We can use Pythagorean theorem because that's a right triangle. If it's not a right triangle, you can't use Pythagorean theorem, but if it is, you always can. So we know that 3 squared plus 4 squared is equal to that squared. What's 3 squared? Plus 4 squared? What's 9 plus 16? 25. And that's going to be the square of this. So what must that be? 5. Now, folks, if you hadn't already run into this, let me tell you, this is one of the handiest right triangles of all time. It's called a Pythagorean triplet, 3, 4, 5 triangle. Always going to be a right angle. Now, I grew up on a farm in Georgia. My dad was an ag engineer by training, but he wanted to be a farmer. So he didn't work as an ag engineer, except everything he did was ag engineering, okay? And we built our own sheds and buildings, storage buildings. We did all that stuff. And when he wanted to make sure he had a right angle at the corner, he took a tape measure, a long tape measure, and did 3 feet and 4 feet and 5 feet. Had one of us stand at each thing. That corner was going to be a right angle. 3, 4, 5 triangle. Except those are sort of short. You can double those. Make it 6 feet, 8 feet, and 10 feet. If your tape measure was long enough. Or even triple it. 9 feet, 12 feet, and 15 feet. all those triangles are going to be right triangles. And you can make sure you got a right angle then, because they always are going to form a right angle. Those are Pythagorean triplets, they call them. Okay? So now, can we finish that? Opposite over hypotenuse will be 4 over 5. You could call that 0.8 if you wanted to. Okay? Cosine would be 3 over 5. Tangent would be 4 over 3. Perfect. In fact, we can do the same thing we did before. Remember, I did them like this. So you can draw a dividing line here, cancel out the 5 and 4 over 3. So what's your cotangent going to be? 3 over 4. Your secant going to be 5 over 3. And your cosecant be 5 over 4. Okay, perfect. That is so easy. I wish I could find a way to make it harder, but I haven't been able to do so. Okay, so maybe if I just turn the light off, that makes it harder. I don't know. So, pretty easy to do. Okay, but don't say the sine of this is 4 because that's the y value. Don't do that. Can sine ever be 4 or after? No, it can't be 4. No. Because it can't be greater than 1. 4 over 5, yeah. Cosine is 3 over 5. Notice, these are always less than 1, okay? And these are always greater than 1. These could be anything. Keep that in mind. All right, that's how we did it. Let's see how they did it. Do it. Do it to it. Okay. By the Pythagorean theorem, start off with that. The hypotenuse is the square root of the sum of the two squares. That will be square root of 25, which is 5. Fill that in, and the rest of it's a piece of cake. The sine is opposite over hypotenuse, which is, what was that, 4 over 5? The cosine, no, they do it right, okay. Cosine is adjacent over hypotenuse, which is 3 over 5. The tangent is opposite over adjacent, taking oats away, tripping on acid, okay, whatever. TOA is 4 over 3. And then they go to cosecant. I don't know why. It's 5 over 4. Secant is 5 over 3. And cotangent is 3 over 4. Remember what angle we're dealing with. Make sense? Just a piece of cake. Okay? Now, in example 1, you are given two lengths, the lengths of the two sides of the right triangle, but not the angle theta. Often you'll be asked to find the trigonometric functions of a given acute angle theta. Okay? To do this, construct the right triangle having theta as one of its angles, thing you were given, and especially if it's one of our favorite angles, these are our special angles, and these are, of course, 0, but I don't even list. But pi 6, which is 30 degrees, 45 degrees is pi 4, 60 degrees is pi thirds. Do those, but you could include 90 degrees as pi halves. You can't do a right triangle with it because it's not a triangle. But we do have Ryan here. All right. So we're just missing Cody and Lindsay. All right. Good attendance class. All right. So here are those, our favorite special angles. Same as they were for our unit circles, so nothing new to memorize or learn here, but just something to keep in mind. Sine of 30, or pi 6, 30 degrees of pi 6, is always going to be 1/2. That means whatever your short side, because 30 is a small angle, okay, the short side is always going to be 1/2 of the hypotenuse. This side is 1, that side is, the hypotenuse is 2. Always going to be half of that, okay? Now, that would also apply then the complementary angle of that is 60, so therefore the cosine of 60 is going to be 1/2. Now, what was the opposite side of 30 is now the adjacent side of 60. So that's going to be 1/2 because that's the short side of the hypotenuse. For a 30, 60, 90 triangle, it's always going to be 1/2. Now for a 45-degree triangle, I would probably start with the tangent because the y is going to be the same as the x, so the opposite is equal to the adjacent, so that's going to be 1. And the same reasoning we did before, these both would be square root of 2 over 2. Okay. And then for 60s, those are just the reverse of these, which is going to lead to something a little bit later. But the tangent of 30 is going to be sine over cosine of 30, which is 1/2 divided by root 3 over 2. The 2's can go out 1 over root 3, which is root 3 over 3. And then the reverse of that is root 3 over 1. Because the 2's go out. And that's just root 3. All right. Those are the special angles we know and love to deal with because we know their values always. On the unit circle, in any triangle, they're always going to be the same. Now, while we're on this slide, I'll go on and say something they're going to come up with later. Notice that the sine of an angle is the same as the cosine of the complementary angle. The co and cosine comes from the complement. And the sine of 60 is the same as the cosine of the complement of 60. Of course, that's true too. There. 45 is a complement of itself. But those are always equal. Whether these are favorite angles or not. If you happen to know the sine of some little angle, know its value, then you know the cosine of its complementary angle because they're the same values. Because of this very reason, the opposite side here of the right triangle here, the opposite side here is the adjacent side of the complementary angle. Because those two angles have to add to be 90, they're complementary angles to each other, so the cosine is the adjacent side of a hypotenuse. Well, that was its complementary angle, that's the opposite of a hypotenuse. They're the same, so they've got to be the same. So that's where co comes from, complementary. Okay. Everybody got it? It's just a little extra yak while y'all were writing. In that box, note that the sine, same thing I was just doing. The sine of 30 degrees, 1/2 is the same as the cosine of 60. That occurs because 30 and 60 are complementary angles to each other, so the sine of an angle is the same as the cosine of the complementary angle. And in general, it can be shown from a right triangle definition. The cofunctions of complementary angles are always equal. That's the shorthand way of saying it. The cofunction of complementary angles always equal. That is, if theta is an acute angle, then the following relationships are true. Theta is acute. The sine of 90 minus theta, which is the complement of theta, is the cosine of theta. The cosine of the complement of theta is the sine of theta. The tangent of the complement of theta is the cotangent of theta. The cotangent of the complement of theta is the tangent of theta. And even here, the secant of the complement of theta is the cosecant of theta, and the cosecant of the complement of theta is secant of theta. That summarizes it. And they don't have to be our favorite angles or anything. Anytime, if this theta was 27 degrees, his complement is 67 degrees, I think. Something, whatever it is. Whatever the complement are, you know those angles are related in that way. Okay. I haven't been turning my page, so let me make sure we haven't skipped any. We did skip one, but we've already done it. Find the values of sine of 45, cosine 45, and tangent 45. From that table, they're already done. And let's go back and do those, I guess. I'm sorry, I wasn't turning the pages, so I should have done this one first. Let's do example 2. Sorry, it's sort of redundant, but we'll do it. Find the sine of 45 degrees. Now, y'all know it already, right? That's not quite 45. That's probably a little better, isn't it? Maybe. Good deal, folks. Just erase everything of value. That's not quite good either. Something like that. Let's just assume that's 45 degrees. That means this length and that length are exactly the same, right? Because if that's 45, this has to be 45, right? And of course, this is 90, okay? Now, if these two lengths are the same, doesn't matter what we name them. So let's make it 1 and 1. Why not? Is that okay? What must be the hypotenuse then? Yeah, the angle between both of those are 45.
Must be greater than 1.
Second?
It's got to be greater than 1.
Okay, I agree with you there. The hypotenuse is greater than 1. What is its value? Name Pythagoras, ring a bell. Square root of 2, right? Because 1 squared plus 1 squared is 2. The square root of that is square root of 2. Okay? So the sine of 45 is opposite over hypotenuse. What would that be? 1 over root 2. And if you don't like root 2 in the denominator, you could write it as root 2 over 2. And cosine of 45 would be 1 over root 2, which is root 2 over 2. And tangent of theta, tangent of 45, is 1. It's the ratio of those two, which is exactly 1. That's what they asked for. That's what we got in Toyota. Okay? Now, the checkpoint is doing the other three functions, the cotangent, the secant, and the cosecant. I'll let you do those on your own. All right, let's do example 3. Is that okay? Can I move? No, y'all are still writing. Let you catch up. By the way, you're absolutely right. Square root of 2 is greater than 1. It's 1.414, so it's greater than 1. You guessed well. Just kidding. Okay, everybody got it? Okay, let's do example 3, because they skipped that one too. It says, use the equilateral triangle shown in the figure. Oh, I'm sorry. They were using the figure I just did. I didn't pay attention to the problem. They did 1, 1, and root 2, and that gave you exactly what we did, because I said, let's just choose it. But this time we're going to do this equilateral triangle. Now that's not quite, but equilateral triangle means the 3 sides are equal length, meaning the 3 angles are equal length, and what would the angles have to be then? 60, 60, and 60, because that's the only 3 angles that add to, same number adds to 180, okay? So that's your equilateral triangle. Now, just for funsies, let's just say that each of these sides is a 2. 2 here, 2 here, and 2 here, equilateral, okay? The reason we do that is let's bisect this side, this angle, making this 30 and this 30. You could be in radians if you wanted to. That would be pi thirds and pi sixths, okay, if you prefer that. That makes this 1 and that 1, right? So now we have a 30, 60, 90 triangle over here, because that bisection is 90 degrees, okay? So since we have all this, the only dimension we don't have is what? This one right here. We're going to have to come up with that. what would that be? Bisecting line. We don't have that.
Would be the opposite.
I wish to.
Okay, this would be opposite of 60. You're right. Why? How could we figure out what length that is?
We do Pythagorean theorem, but
Oh,
we
yes.
leave out leave out B.
Okay, leave out b. So this will be 2 squared minus 1 squared. 2 squared minus 1 squared. What's 2 squared? Minus 1 squared. That'd be 3. And then this would be the square root of that, which would be square root of 3. So now we know what that side is. This is root 3. All right. So now can we come up with the, which did they say? The sine of 60. Okay. Here's your 60 degrees. As someone just said, the opposite side is now root 3. And what's the hypotenuse? What is that one? 2. Okay, there we have it, root 3 over 2. Which I think is the same thing we had on the unit circle, wasn't it? Isn't that amazing? Okay, trig is like that. The second one they asked for is the cosine of 60. And what would that be? Second? 1 over 2, you're absolutely right, because it's the adjacent side over hypotenuse. And then they asked for the sine of 30. And what would that be? Here's your 30 degree up here. What would that be? Anybody? Pretty easy. 1/2, okay? And I think the last one they asked for was cosine of 30. And what's that? Anybody? Root 3 over 2. And then this is what we were saying earlier. The sine of the complement of an angle is the same as the cosine of the angle. The cosine of the complement of an angle is the same as the sine of that angle. Yeah. Got it. That led us to the table. Sorry, I jumped ahead. Now, let me also say this. For a 30, 60, 90 right triangle, and draftsmen use these a lot when you're doing things, because they have these really special things. Whatever the short side is, see, this is the short side, there's the medium side, there's the long side, right? The short side is always, always, always half the hypotenuse. Always. And that leaves the medium side to be square root of 3 times the short side, which is square root, a little bit weirder, but square root of 3 times the short side. Okay. Always. Okay. So that's good things to keep in mind. Okay, I think we're ready for example 4 now. Let's see. No, they didn't do example 4 either. So let's go back and do example 4. How are we doing on time? I'm watching my pocket, huh?
10 minutes.
How many?
10.
10, okay, good. Sometimes this class flies by way too fast. Okay. Yeah. Okay, so let's do example 4, I think it was. All right to erase? Okay. Use a calculator to evaluate the secant of 5 degrees. Since we were doing this kind of problem anyway, 40 minutes and 12 seconds. Huh? We weren't doing anything close to this, but we can do it. It's just a little bizarre place to put it. Now, how are we going to do this? There's a couple of ways. I want you to tell me what would be your thinking on it. Okay. I hate to take over, but I will, okay? I want to get everything in degrees, okay? Because calculators are looking for degrees. They're not looking for minutes and seconds. Now, maybe you have a calculator that will accept them, and so get in that mode and do it, okay? But since I don't have one that does that, I need to get this as fractions of a degree. So, what fraction of a degree is 40 minutes? What fraction of a degree is 40 minutes? How many minutes are in a degree? 60. Okay? It's like 60 minutes an hour, same here. So if 60 minutes are in 60 minutes in a degree, 40 minutes would be 40 over 60. So I'm going to write this as secant of 5 degrees plus 40 over 60 degrees. That's a strange way to do it, but I'm going to. Plus, now, how many seconds are in a minute? 60. And how many minutes in a degree? So how many seconds in a degree?
3,000.
Not quite that many, is it? Yeah, well, you're right. It's 60 times 60 is 3600. 3,600. So this will be 12 over 3,600, or 60 squared. Okay? And that will be a degree now. So the first thing I'm going to do is that calculation. Okay? All right. Now, that won't help me a lot because I still don't know how to take a secant. Or do I? What is a secant?
It's the reciprocal.
Cosine, exactly. So here's one way to do it. This is 1 over the cosine of 5 degrees plus 40 over 60 degrees plus, you don't have to write degrees down there, I'll just do it, 12 over 3,600. And that'll be in degrees too. So basically I would do 1 divided by cosine of 5 plus 40 divided by 60 plus 12 divided by 3,600. Close that parentheses, hit E. Okay? Or you could just do cosine of blah, 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 blah. Close that off and then hit the 1 over x key or x minus 1 key. If you like that better than 1 divided by. Doesn't matter, whichever you prefer. Anyone do that? See what you get? First, I'm going to ask you, what kind of number do you expect?
We got 1.0049.
Does that sound at all reasonable? Secants are always greater than 1, and that's greater than 1, so at least it makes me feel warm and fuzzy. Now, this is just a little bit more, this is a small degree, and at 0 degrees, cosine is 1, secant is 1, so this is just a little bit more than 1. Yeah, I feel really warm and fuzzy. So what did you say it was?
1.0049.
Wow, I didn't know it was that small. 49 something another. Okay. Okay, you'll never get an exact answer, hardly. Okay. Those special angles you will. So, yeah, they got 1.0049166. Okay. Good deal. Any questions on that? All right. All right. Now let's go to our trigonometric identities, or can we? Oh yeah, we've got a few minutes, don't we? Okay, let's do it. Reminding ourselves what our trigonometric identities are. Guess what? They're the same as they were for unit circle. The trig identities are the trig identities. A sine is always 1 over cosecant. A cosecant is always 1 over sine. A cosine is always 1 over secant, and a secant is always 1 over cosine. And a tangent is always 1 over cotangent, and a cotangent is always 1 over tangent. Now, I said always, really not quite always. This is not true when sine is 0. Okay, that's not true with cosine of 0, and that's not true with tangent of 0. I don't have to say it here because cosecant is never 0, and secant is never 0 with cotangent. Now, the quotient identities, I also like calling these ratio identities. Okay? The tangent is always sine over cosine, cotangent is always cosine over sine. They come before 2. And then here are Pythagorean identities. Get to know these. These are very, very, very helpful. You'll be using these forever. Y'all are all continuing in the calculus, right? You'll use them there. You'll use them everywhere. Okay? And the easiest of these to remember is this one. Sine squared plus cosine squared is always 1. Now, does that seem bizarre? Well, let's think. Since we're dealing with with triangles, with right triangles, you tell me what sine is. If you're dealing with old hippies or hens or hags or so's or co's or cos or whatever, what is sine? Opposite over hypotenuse squared plus adjacent over hypotenuse squared. Well, let's just leave it alone and see what it comes up being. This will be opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. Well, that has a common denominator. That will be opposite squared plus adjacent squared over hypotenuse squared. But what is the opposite squared plus the adjacent squared? Say again?
I said, what did you say? What did you say?
Okay, what is the opposite squared plus the adjacent squared? Draw your right triangle. Draw your right triangle. There's your theta. Okay? Here's your opposite. Here's the adjacent. What is opposite squared plus adjacent squared? If indeed that is a right angle. It doesn't look like it, but let's say it is. What is opposite squared plus adjacent squared? Okay, what if I didn't call that opposite? What if I called that B? Say again?
B.
Okay, if I call it B, what would this then be? Oh, yes! So what is that? A squared plus B squared is? C squared. But now I'm calling this O squared, I'm calling this hypotenuse. So that's 8 squared, right? Agree? Okay, so we got O squared plus A squared is 8 squared. And what's 8 squared over 8 squared? 1. Always 1. Okay? Doesn't matter how small the triangle, how big the triangle, it doesn't matter. It's always going to be 1. How small the angle, how big the angle. As long as they're both acute angles, they're going to be 1. Okay? And we ran out of time, I take it, because I see people packing up their bags. Okay. I do want to do just a little more on this. So what I'm going to do is we're going to start with that Pythagorean identity next time. Okay? And we'll go from there. Okay? We'll get this in its place. All right. Homework exercises here will involve any of the odds, 5 through 9. They're all at calcchat.com. 5 is at CalcView. Do 11 or 13. They're both at CalcChat. Let's hold off 15 to 19 until we get a few more done. Okay? Good deal. Any questions? One other thing. Have a good weekend. Of course, doing trig problems will make it good, right? Yes.